gidiyor değil mi? Güzel. Okay. We will continue with chapter 2, processes and threads. You got your first assignment, first homework number 1, which is about simulation of CPUs and the processes. So start. I guess you have more than 2 weeks, maybe 3 weeks, around 3 weeks. You should start early because this is your first homework in this course, and you would know what kind of problems you would have. And soon we will email you about the instruction how to submit your homework, because we will follow very strict rules. If your program doesn't compile, if your program doesn't do certain things, we will not grade them. You should run some of the examples without any problems. If they don't follow the rules that we send to you, then we will not grade your homeworks. So you should be careful about how to submit your homeworks. Did you read the homework? Anybody read it? Any questions so far? So ask your questions early, okay? Last 2, 3, 4 days I will not answer any questions, okay? Because 3, 4 days are not enough to complete this homework, and it is better to ask questions early. Okay, then we will continue with chapter number 2. One more thing. Homework 1 is the first homework, and the rest of the homeworks, homework 2 and 3 and 4 and 5, whatever, they will depend on homework 1. So if you don't complete homework 1, you will not be able to complete the other homeworks, and I will not let you use somebody else's homework or code. It will be treated as cheating. So whatever you do, you complete this homework, okay? Even if you are late, you should complete this homework. It is important. Okay, if there are no questions, I will continue with the processes and threads. Thread simply means, this is the standard definition, program in execution. Program in execution. Okay. If you have a program, just a program written program in C or some other language or in assembly, it is just a program. When you start executing the program, it becomes a process. Because when a program runs, okay, when a program is in execution, you don't have just the program itself. You have the program counter, PC. You have the stack. You have the stack pointer. You have your variables. You have the values of your variables. So everything with the program becomes program in execution. It becomes your process. Okay. So when we talk about a single process only, it is not that interesting, but we most of the time in operating systems we use multi-programming. Okay, multi-programming. What does multi-programming mean? Somebody tell me. Multi-programming. What does it mean? Multi-programming. Somebody is saying something, I don't understand what he is saying. Yes?
Aynı anda birden fazla fonksiyon çalışması, yani sadece bir main üzerinden değil, farklı parçalarında çalışması.
Aynı anda birden fazla fonksiyon dersek birazcık sınırlamış oluruz.
Birden fazla prosesi bir kodda aynı zamanda aralığında çalışması, ama bunu birden fazla kodda da yapabilir.
Birden fazla?
Birden fazla kod kullanarak da programı.
Birden fazla kod ne demek anlayamadım.
Kod.
Rekörsif gibi mi yani? Multi-programming simply means having more than one process exist on the CPU. Since if we have a single CPU, we can still do multi-programming, because a single CPU can run a program, can run a single process at the same time. But if we have more than one process exist on the memory, and if the CPU is switching back and forth between these processes, then we have multi-programming. So if we have more than one process exist on the memory, if we have more than one process running on our system, then we have multi-programming. Okay, so we think that computers usually run multiple programs simultaneously, which is most of the time wrong if we have only one CPU. They just appear that way because they cannot run, a single CPU cannot run more than one process, okay, at the same time. So what does it do? It just switches between processes, right? This is my single CPU, single core CPU. It runs process number 1, just a little bit. Then it does something else. Then it does process number 2, then 1, then 3, then 2. It goes that way. So it appears that this CPU is running more than one process at the same time, but it is actually switching back and forth between the processes. So exact time pattern varies for each process. I mean, nobody can know what kind of. It is very difficult to know what kind of sequence this CPU will follow. 1, 2, 1, 3, or 1, 3, 1, 1, etc. So we would not know. It is a very complicated thing. It depends on the scheduling. It depends on the how frequently the processes are blocking. Okay. There are idle times too. See, these are the idle times. Why are they idle? Why CPU is not doing anything? Question?
No one tries to do anything.
Who is talking? Yes.
No one tries to do anything. It's
Why?
just idle.
Why would your process don't do anything?
For example, it could be an error.
Yes. For example, if all of these processes are waiting for something, are waiting for some disk reading from the disk, or are waiting for some packages from the network, right? So nobody has anything to do. That's why CPU can sit idle even though there are 3 processes exist in the memory. It can happen. It can happen. Sometimes more than one process tries to use the same CPU. Sometimes no process can do anything. So the CPU can still sit idle even though we have more than one process exist on the same memory. So this is multi-programming, and multi-programming is a very important part of an operating system, especially if you have more than one core, if you have more than one CPU or system. Multi-programming becomes even more important. Okay, so this is our process model. On my memory, I have 1, 2, 3, 4 processes. Okay, and my CPU switches from A to B, B to C, C to D, then back and forth again. So it is multi-programming with 4 programs. It seems to us that each process is running on a separate CPU. It looks that way, but in fact they are sharing the same CPU. So each process has its own, it looks like each process has its own CPU. With the CPU, you have your registers, right? Registers, you have your program counter, you have your status word, you have your stack, okay? So each one has its own data structures and this kind of data. It seems that way. And it's a it's an abstraction of the CPU, so that I have 4 virtual CPUs. I would see it as a 4 virtual CPUs. In fact, the time is sliced between these processes, and I have a single CPU. Okay, so that's the main idea of multi-programming, and with the multi-programming, we will look at this idea of processes in more detail. So When we talk about the processes, let's talk about this process creation. When do we create processes? The book says there are four ways of, there are four causes for creating, making new processes. Okay, the last one is kind of is not familiar, very familiar for us. We will look at it, but the other three are very, very familiar. The processes are created when the system is initialized. Okay, that's one place where we initially initialize or make new processes. When the system starts up, okay, Linux starts with this process init, okay, initialization process, okay, that's one thing, and the initialization process starts other processes, and that's where the second cause of the process creation is, it comes to the picture. Execution of a process creation system call by a running process. If your process runs a special system call, then you would make another process. For Linux and for Unix, what is the system call? How do you create a new process? What do you call? You call the function named fork, and that function named fork calls the system call fork, and it makes a new process. In Windows, in other systems, it is all different. That's the second way of creating a process. The third way of making a new process is a user request. For example, from the shell, the user types ls. When the user types ls, a new process named ls is created, and it does its job, whatever it is job. When it is done, it is done. Okay. So actually, this one is kind of, it falls under the second way of creating the process, because when the user initiates something, it initiates something from within a process. So the process is actually calling another process creation call. Yes?
Hocam bu fonksiyon bunun içerisinde biz yazamaz mıyız? Kendi fonksiyonumuzu yazıyoruz.
Anlayamadım.
Seviyesinde mi çalışıyor?
Fonksiyon? Fonksiyon? Bir daha sorsana, sonra anlamadım.
Fonksiyon. Biz bunu kendimiz yazamaz mıyız? Kendimiz for fonksiyonu yazamaz mıyız?
İkinci ödevinizi yazacaksınız yani. Yazarsınız. Yani yazmazsanız zaten bu dersten geçemezsiniz. Yazabilirsiniz. Yani çok karışık bir şey biliyorsun değil. Yaptığın zaman göreceksin ama detayları var tabii. Sistem genişledikçe işte fork'la beraber proses yapmaya başladığın zaman şunu olacak, bunu olacak, bunu olacak falan filan, onların hakkında daha fazla konuşacağız. Fork'un ne kadar karmaşık bir şey olduğu hakkında. Yani eğer CPU'nun çok basit bir, if you have a very simple CPU, okay, like the CPUs from the 80s, making a new process is not that difficult, because all you need to do is you have a program, you load your program, you have your data section and the stack section, and you need to initialize your register, etc. You don't have anything about the virtual memory, you don't have anything about the cache, okay? You don't have anything about the complicated file structures and the child processes, etc. Right? For the very simple operating systems, like the one you are writing, okay? Writing a fork system call is not that difficult. Okay? It is simply copying your parent process and informing the operating system about the new process. That's it. Okay? So it's not that difficult. But if the system gets complicated, like today's operating systems, Windows or the Linux, then writing fork takes some time. Okay? It takes some consideration. Depends on the operating system. Yes. So fork is not a. You will write something similar to fork in your homework number 2 or 3. Okay. So, and the last one is the initialization of a batch job. What's a batch job? Batch job.
Bekletme mi hocam? Proses.
Hayır. Block değil, batch. Batch job, yes.
Arkada sürekli aynı işi yapan işlem.
Not background job, it's batch job, batch job. We usually don't have batch jobs on our PCs. Mainframes have batch jobs. Remember in the 1960s, in order to keep the CPUs running all the time, computers running all the time, without any idle time, you have many batch jobs, one after the other. Okay, one after the other. One batch job completes its job, and the next one continues. Okay, so batch jobs are usually they are run on the mainframes. Very similar jobs running one after the other. They are very large jobs. So if one batch job finishes, the others can start working. Or if the operating system thinks that CPU is sitting idle, the CPU operating system can start another batch job in parallel with the other batch jobs. Okay, so they are usually used with the servers and the mainframes. So in PCs we don't have anything very similar to batch jobs. That's why I put them in a square. So system initialization and number 2, execution of a process creation from another process are the two main process creation causes. Okay, how about the process termination? How do we terminate processes, or how many ways we can terminate the process? One way is normal process termination. Okay, voluntarily. The process says that I am done. Okay, so it calls this exit function. An exit function makes the system call exit. Or second one, the process voluntarily says that I am done, but there is an error. So it exits with something like this. The third one is involuntarily the process terminates. When does this happen? This happens when the process does something illegal. For example, it tries to do this divide by 0. Okay, when it divides by 0 involuntarily, there is a fatal error. Okay, there is no recovery from this. So the involuntarily process is terminated. Or finally, the process might be killed by some other process. Okay, can you give me an example for this one? This is an involuntary again. The process does not terminate by itself. It is terminated by somebody else. Arkadaki arkadaş şu bilgisayarını kapatsan orada. Bu dersle alakalı bir şey yapmadığını görüyorum burada. Okay. Biz bir şey söylüyorduk. 4 ile ilgili. Give me an example about killed by another process.
Signals in Linux, kill signal, seek10.
Yes, if somebody calls this function with your process ID number, then your process will be killed if I have enough permission, right? If I have enough permission, if I call this kill signal, okay, if somebody sends a kill signal to your process with the correct process ID, your process will be killed. Or something else, yes.
Hocam bu programları hani öldür diyoruz ya biz hani kendimiz yaparak. O zaman da aynı şey mi oluyor?
Zaten o işte.
Yani görev yöneticisinde falan açık. Ondan bahsediyorum.
Görev yöneticisi sadece bir grafiksel arayüz GUI, tamam mı? GUI'de sen bunu öldür dediğin zaman esasında GUI alt tarafta böyle bir tane system call çıkıyor. O da öldürülüyor. So if I have enough permission, I can kill processes or terminate processes. Or if I am shutting down my computer, the operating system terminates all the processes one by one, right? It kills all the processes one by one. Or if I am logging out, all of my processes are killed by the operating system one by one. So these are all involuntary termination of the processes. Okay. So let's talk about the processes again. Let's go into more detail. Let's talk about the process states. Okay. The process can be in one of these 3 states. The process could be running. What does it mean running? Actually using the CPU at that distance. So the process is actually is using the CPU. CPU is executing the program of the process itself. That's one of the states of the process. The second state is the process ready. It is not running, okay? It is not running, but it is runnable. Temporarily stop to let another process run. Okay. So how do I get into this state? I will talk about it. And there is this blocked state, unable to run. So the difference between ready and blocked. What is the common thing between ready and blocked?
Not using.
They are not running, right? So that's the common thing. They are not running. Okay. But the difference is between them. If the process is not running but is ready to run, then it is the ready state. If it is in the block state, then the CPU cannot run it. Okay. CPU cannot run it. It has to wait until something happens. Okay. So these are the three states that the process can be in, and this is a very nice picture. Okay. Running, ready, and blocked. Okay. So when does one happen? When does the process becomes blocked? Let's talk about this number one. Yeah, that's true. If the process needs some data from the keyboard, let's say read something, so it is waiting something from the keyboard or from the disk. So it waits blocked. It cannot continue. It is in block state. Okay, it is in block state. How about number two? When does the running program becomes ready, from running to ready? When does it happen?
Operating system switch processes because one process might long